In this video, we're going to look at how we can combine these circle theorems and answer some of the more difficult exam-style questions that we might get for our GCSEs. So we'll look at a few different strategies in this video. And the first one we're going to look at is chipping away at a problem from angles that we know to try and find the angle that we're after, and sort of breaking it down into bite-sized chunks. And so we have an example here, example 1, and we're asked to calculate the size of this angle. Now, you might notice that the angle we're after isn't drawn in our diagram. So it's really important that you understand what this notation means. So if we're given an angle, we'll often be given it as just a string of 3 letters. And the angle is always the one in the middle. So we're after the angle that's at D. And we'll have a look at how we can trace that out. So this means we start at A, we go to D, we end up at B, and it's that angle that we've traced out, and that's the one we're after. So if we start at A, go to D, and end up at B, it's this angle here that's between AD and DB. So that is the angle that we're after. I might just call that X. Okay, so now we know what we're after, we need to start chipping away at our problem. I've said this before, often with a more complicated problem, it's easier to forget about what we're aiming for and just think about, well, what can we work out? What information do we know is going to allow us to get somewhere with this problem? So forget about the X for now, and think about what things can we do? What circle theorems can we apply? And now the first thing you might have noticed was that we have a cyclic quadrilateral here. So that gives us a bit of an inkling as to a way we can go, because as we know, opposite angles in a cyclic quadrilateral add up to 180 degrees. So if this angle here is 107, then I can work out this angle down here. And now in an exam question, particularly one where we're using lots of different circle theorems, and generally to be good mathematicians as well, we need to be writing what we're doing at each step. So the first thing we're going to find is we're going to find angle, well, we're going to try and find this angle here, which is angle DAB. So we can find DAB, and we're using the opposite angles cyclic quadrilateral circle theorem. So opposite angles in cyclic quad add to 180. So let's work that out now. So we have 107 plus this angle here. So 107 plus angle DAB is equal to 180. So we know that DAB is equal to 180, take away 107, which is 73 degrees. So that tells us that the angle at the perfect DAB is 73 degrees. Okay, so 73, let's draw that on our diagram. Okay, so what else can we use? Well, we've got a tangent, and if we look closely, we've also got a triangle. Now, which circle theorem relates tangents and triangles? 100% correct. It is the alternate segment theorem. So let's use the alternate segment theorem. So that's 42. So I know that this angle here, remember they're pointing to both to the right, they're both pointing in sort of the same direction. I know that that angle here has to be 42 degrees as well. So let's make sure we get that written down. So ABD. And we're going to use the alternate segment theorem. And I know that ABD is equal to 42 degrees. Okay, so now we're honing in on this problem. We're honing in on the value we want. So now I've got X, and I notice that in triangle ADB, this x is the only angle we don't know now. We know the other two angles, so we can work out what x is. So we can work out ADB because angles in a triangle add to 180. So I know that x plus 73 plus 42 are equal to 180. So then 73 plus 42 is 115. So I get x plus 115 is equal to 180. So then to work out what x is, I just subtract the 115. That gives me 125 degrees. Oh no, sorry, 55, 55, 65 degrees. So x is 65 degrees. Now remember, we need to write it. We've been asked for ADB, not x. X is something we've put in to make the algebra a little bit easier. So our final answer has to relate back to what is referred to in the question. So ADB equals 65 degrees. Okay, so on to our second example. Now this time the strategy that we used in the last example isn't going to really work. We're given this angle 57, but there's not a huge amount we can do with that. It's not, we might be thinking that it's in the centre, it's an angle in the middle, but there aren't any other angles coming from these 2 points around the edge, so we can't use this circle theorem. It's not part of any quadrilateral or any triangles, so there's not really many places we can take that 57. So we can't start here and chip away at the problem, we have to use our second strategy, which is to start at our unknown and see how far we can get that way. So what we can do is, if we look at x, we need to think, what angles can we write in terms of x? Well, the first thing we might notice is that this forms an isosceles triangle, and so this angle here is x as well. If at any point you do think you can spot where we need to go, obviously feel free to pause the video, and then at the end you can check your answers to see how you've got on. Okay. Anyway, we've got two x's here. So now we need to think, well, we've got two x's, we know two of these angles in a triangle, and we can work out this third angle. So let's do this one in green. So this angle here, well, how can we write that in terms of x? Well, if we knew what these angles were, if we could give a number for these, we'd add these together and subtract it from 180, and that would tell us this green angle. And we can still do that even though they're letters. So if we add these two angles together, what do we get? Well, we get 2x. So then to work out this green angle, we simply do 180 minus 2x. And that gives us a value, or an expression, for that green angle there. Okay, so let's see how much further through this we can go. So now we've got an angle here, and we've got this angle that's on a straight line. Okay, so if we know one angle around a point on a straight line, we can work out the other one. So what we need to do is, I know angles on a straight line add up to 180. So if I do 180, and then I'm going to take away this angle here. Now it's important that we put brackets around it because we're subtracting it. 180 minus 2x, and that's going to give us our blue angle. So let's work this out. So 180 take away 180 is just 0, but then the minus 2x, we need to take that away as well. So if we take away negative 2x, that turns into positive 2x. So I know that this blue angle here has a value of 2x. Okay, now we can use one of our circle theorems, the isosceles triangle one. So if this line is the radius of a circle, and this line is the radius of a circle, then they're the same, they have the same length. Which means this angle is the same as this angle, so that's also 2x. Okay. Nearly there now. So we've got one more angle we can work out. So we can work this angle out because we know expressions for two of the angles in this triangle. So again, to work out what this angle would be if we were given these as values, we'd add them together and subtract it from 180. So this pink angle, so this was to work out our blue angle. This is now to work out our pink angle. So our pink angle, again, we add these two together and subtract it from 180. I'm going to do 180, and we're going to take away, now if we add these two together, that gives us 4x. Okay, and that's equal to our pink angle, so let's label that on. 180 minus 4x. And now we're really getting somewhere, because we know these three angles that are on this straight line. So I know that these three angles have to add up to 180. So then to work out what x is, I'm going to do 57. So to find x, I'm going to do 57 plus this pink angle, which is 180 minus 4x, plus our third angle there, x. And that has to be equal to 180. Okay, so we're into the final steps now. So let's simplify this down. So 57 plus 180 is equal to 237. Take away the 4x plus x is take away 3x. And that's equal to 180. Okay, right, this is an equation we should know how to solve now. So if I add 3x to both sides, I get 237 equals 180 plus 3x. Let's now subtract the 180. And well, I know from before that 57 plus 180 is 237. So if I take the 180 back away, I get 57. 57 is equal to 3x. So my final answer is x is equal to 57 divided by 3. Well, 60 divided by 3 is 20, so 57 divided by 3 must be 19 degrees. So that is our final answer for x. So slightly different strategy. Instead of starting with the angle we know, we start with the angle we don't know. Okay, so our last strategy is proof. Or the last sort of question we might get is proof. So what we need to do in this example is we need to prove that AC is a diameter. Now we're not given a lot of information here, so we might be thinking, I'm not really sure how to go about doing this. Don't worry though, because we can sort of have a bit of a think about what would we need to know to prove that AC is a diameter. What do we need to know for AC to be a diameter? Well, looking at our circle theorems, the only one really that involves a diameter is this one here. So it would be really nice, we want to show, and if you can spot something that will prove it, it's really useful to write it down so we know what we're aiming for, but we want to show that ADC is a right angle. If I know that this angle here is a right angle, then I know that this is a diameter because we have this circle theorem, a triangle in a semicircle is a right angle triangle. So if we can show that ADC is 90 degrees, that'll do it. Okay. It's not always obvious what you need to show to work out an answer or to prove something, so you don't always have to start there, but if you can spot something that'll help, then it's worth just keeping it in the back of your mind. Okay, so let's have a look here then. So we have a cyclic quadrilateral that's split into two triangles, and we've got a circle theorem about a cyclic quadrilateral in the opposite angles add up to 180. So we might be able to use that fact. So opposite up angles in a cyclic quad add to 180. Okay, now I know that BAD, this whole angle here, and BCD, this whole angle here, because of this rule, have to add up to 180. So I know that BAD plus DCB is equal to 180. Okay, now BAD is 2x, DCB is 2y, and I know that that has to be equal to 180. And now what we can do is, I'm aiming for something that's equal to 90 degrees, and I spot that actually we can divide this whole equation by 2 to give me something that involves 90 degrees that then we can go on to use. So if I half this equation, well, 2x becomes x, 2y just becomes y, and 180 becomes 90. Okay, now we're getting somewhere because I know that x plus y is 90 degrees. And if we look at triangle ACD, well, the angles in that triangle have to add up to 180. So in triangle ACD, and they add to 180. Now let's call this angle here, let's give it a letter. It's often nice to think about these things with letters. Let's give it an A. We've got x and y are a letter, so let's give that a letter A. So the three angles in this triangle have to add up to 180. So I know that A plus x plus y is 180. But I also know that x plus y is 90. X plus y is 90. So now I know that A plus 90 is 180. Which leads me to work out that A is 90. If I subtract this 90 from both sides, that leaves me with A is equal to 90. Which proves it. If A is equal to 90, then this is a right angle triangle, which means that it must be in a semicircle. AC must be a diameter. Now I have to actually write that down. Generally in maths, if you've proven something, you don't want to leave it to the person that's reading to figure out what you've proven. It's always handy for you to write down exactly what you've proven. And a bit more cynically, in an exam, you won't get a mark unless you do. So we're looking for to prove that it's a diameter, aren't we? So ADC equals 90 degrees. And so because angles in a triangle are angles in a semicircle are right angled, the semicircle ACD, or the sector ACD must be a semicircle, which means that AC must be a diameter. Okay, and there we have it, our three strategies for solving these more complicated circle theorems problems.